We're going to talk about the phenomena that you're probably undergoing right now. Those of you who deal with a lot of Boatanchor radios, you'll notice that the input voltage to those radios is not what you're getting out of your receptacle. So what's the consequences and how do we be able to handle that? So let's proceed on. When Boatanchor class equipment was manufactured, the incoming AC voltage was likely lower than it is now available in your shack. Equipment had specific and lower voltage requirements such as filament use, plate voltage for tubes, pilot lights, etc. The use of such equipment on present-day voltages available at the receptacle level results in higher than normal voltages inside the equipment. This out of normal condition generally results in increased heat. Additional stress on active devices generally shortens the component life. Such components are becoming somewhat harder. When I was a teenager, I had one of the first radio and TV licenses to fix stuff like that for my age. And I remember going down, and I like Drake radios, right? What's the final that's used in Drake radios? 6JB6s, the horizontal output of the RCA first color television. So, and that TV used 6JB6s like you would eat popcorn in a movie. So I would go down and I would buy a sleeve, which was 5 tubes, and I do that maybe 2 or 3 times a month, several sleeves at a time, and I was paying a whopping 67 cents a piece for 6JB6s. I was horrified. What kind of smoke was inside of those tubes?
Not much.
I can tell you. And now, when you can find them, they cost about 30 bucks a piece. So, becoming somewhat harder to find and an increased cost is an understatement. Let's see what we can do about it. Let's review the issue and see what we can handle with it. In the earliest 20th century, now, I put that there because I realize that most of the people here understand the concept of time. The early 20th century was a long time ago. Cities began to electrify with the new electric services. At the beginning, for residential loads, there were 2 systems. One by Edison, about 100 volts, 2-wire DC. The other one by Tesla, 100 volts more or less, depending upon how he could run his generators. Single phase AC, 100 volts. History will show, and it's an interesting history, if you want to do some really nice, quiet reading, look up how it was determined, the battle between the Edison system and the Tesla system is really interesting history. I wanted to be a history major when I went to college, and I got turned to the dark side, and I wasn't a history major, but I love it. In the beginning, the load was mostly incandescent lighting. Where did that come from? Edison, right. Not only do you sell the stuff that can use the energy, but you create the energy and do that. I mean, you know, he was pretty smart. The nominal 100-volt system was adequate for this purpose. As new loads and utilizations were realized, especially in motors, where'd the motors come from? Tesla. That's right. New distribution voltage were needed. Increased power draw on the existing lines soon led to a maximizing of the current carrying capacity of the distribution system. I don't want to get too much math in here. Power equals volts times amps, right? So if I got to get more power to a location, I have 2 variables. I can vary the voltage or I can vary the amperes. The wire that's going between point A and point B is a given wire. It can only handle so much A. So the only variable that you really have left is the voltage. You want more power, you increase the voltage, and that's what was happening. So instead of changing the distribution wiring, they started inching the voltage back up. Electrical industry was maturing. That's an interesting word. And in 1899, it was realized that changes would need to be periodically made to keep up with this new energy source and its use. The AIEE, American Institute of Electrical Engineers, Standardization Rules of 1899 set up the framework where this could happen. Transformer voltage, I realize that some of you may have done that reading originally, but just bear with me. A transformer voltage standardization report was issued in 1922. This was sufficient for a while, but loads were increasing, and as loads were increasing, what was happening? The voltage was rising, right? The NEMA, National Electrical Manufacturers Association, issued the publication 100 in 1930 titled Preferred Voltage Ratings for AC Systems and Equipment. You could probably write a standard and give it any title you want. This lasted through the war years, but again, revisions were needed. Why? They had more things to power by electricity than they had services to it. 1949, NEMA publication 117. You notice NEMA went from 100 to 117. Addressed again the issues, and in 1954, let me see if 1954 subtract 1949, carry the one, wow, that was a lot of years when they were thinking about this. The standard was adopted. The voltage at that time were 115 volts at the receptacle. 1954, 115 volts. I'd say who has a Cosmophone 35, but there'd be only one person in here that would raise their hand besides me. It was 115 volts, right? Richard, you got a Cosmophone 35? Oh, excuse me. I'm sorry, you have two. The voltage at that time was 115 volts, while the standard stated that 120 would be the distribution voltage at the receptacle. The adoption was not immediate, and changes were slow. Why? Because the electrical utility had to take time to generate to this new standard. They took time to create the specifications for distribution transformers. This wild idea of three-phase power was coming up. They had to do all that. The standard is now called ANSI C84.1, adopted operating ranges for the distribution systems in an attempt to address the increasing use of electrical energy. Higher distribution voltages and step-down transformers came to be a normal design mode for large loads. 54 and again in 75, new voltage ratings, primarily for motors, appeared, and a range of voltages allowed for the distribution system was given. This was the first time that a range of voltages were given. This was designed to end the tendency for a slow increase of voltages in the distribution system. And to that effect, it worked. For the receptacle end of, this is where we come in, for the receptacle end of the revisions, the distribution was allowed. You need to read this along with me because you got to grab this hold. Was allowed to range from 106 volts at the minimum to a maximum of 127 volts. Let's read that again. Was allowed to range from 106 volts to 127 volts. This is what from a nominal 12208 three-phase wide distribution system. This affected how transformers were made and gave long-lasting standards to the manufacturers to use in the design of input voltages for their critical. However, in the critical Boatanchor range of equipment, the standard was 115 volts, and by golly, that's what they designed to. We want 115 volts in our equipment coming in, and if you do that, everything is fine. Nick, when's the last time you measured voltage in your house? What would you have?
125.
125. I've measured as high as 128 in mine, and as low as 122. It depends upon whether Nick is transmitting or not. So if the range is plus or minus 5%, then assuming the same range would be applicable for the 115 volt standard, the range would be 109 to 121 volts at maximum for the time when the 115 volt standard was applicable. Therein lies the issue. With the now nominal voltage of 120 volts, go home and measure it. I bet you don't have 120 volts.
That's right.
The upper range of the older equipment is already met at the 115 volt standard. So if the 115 volt standard, the upper limit was 121 volts, and Nick has 127 volts, what's happening to his equipment? The question then begs, what's the effect for a fixed 115 volt AC input on the now standard that allows this voltage to go to a maximum of 126 volts? Let's look at several factors. Filament voltage. Some tube manufacturers, some state, some say nothing about it, that the filament voltage is plus or minus 10%. For a 6.3 volt filament, you can go from 6.93 volts as a maximum to 5.67 volts on a filament, plus or minus 10%. The filament voltage in the out of normal high range increases the temperature of the tube. Remember, in Boatanchor radios, the source of smoke is mostly contained in the tube. So if you wreck your tube and you, metaphorically speaking, let out the smoke, it ain't gonna work. And it might not be the problem of the radio other than the fact that you cramming down 120 things on a 115 volt throat. What happens is that the temperature goes up. Now, I'm going to go back to your third grade tube construction classes that you, excuse me, Ron, yours was in the second grade, I understand. He went to one of them really fancy schools. Tubes are manufactured with a device, which is a chemical device called a getter inside the tube. Contrary to popular opinion, tubes are not a perfect vacuum. You got little metal pins that go in and out of the glass pins. Sometimes you got one going out of the top. And those seals are not perfect. So there can be a small migration of air into the tube. Likewise, the metals that are used for the manufacture of the tubes, when you heat them up, will basically outgas. So this getter is a device that basically absorbs all of that air contamination. What happens when the getter is exhausted?
It don't get no more.
Thank you, Ron. And thank you for that clarification. When the getter is full, what happens to the tube? It becomes gassy. You ever have a tube that becomes gassy? Especially ones that run firecracker hot? Who's got an R4B here? R4B uses a 6EH5 in the audio output. A 6EH5 is a fire hazard. First of all, you can't grab it. If you put a glove on it, it's the only tube that I know that's got some of my fingerprints on it. So if the tube has a manufacturer's tube shield to prevent the transmitting or receiving of spurious signals, then that shield must have the ability to dissipate the heat away from the envelope. You open up an old radio. For example, Richard, the Cosmophone 35. Open up one of the two radios that you have. And you open it up. Every tube, except for the final, has a tube shield on it. Is it needed? Probably not. So they put tube shields on everything just in case one of them might get a little squirrely, and for the tube next door to it, it would give them some things that would turn the purple green. It doesn't really make that much sense. There are some functions that would benefit from a tube shield, but a lot of manufacturers put tube shields everywhere. Anybody open up an R390? Tube shields everywhere. The typical shiny metal tube shield does the opposite. It does not dissipate, but rather holds the heat in, thus increasing the envelope temperature of the tube. There's an interesting set of arithmetic in physics called Blackbody Radiation. Ron, again, I know it was second grade. For me, it was fourth. And Blackbody recommendations theory has a set of arithmetic that the temperature is color sensitive. When you go down to the tropics in the summertime, the people are wearing what color of clothes? Light, right? Why? Because the light reflects the heat. In the wintertime, John, where you're from, in Minnesota, what do they wear in the wintertime?
Well, in Michigan, we wear
Michigan.
winter clothes.
Yes,
Usually dark color.
dark color. And that was an unpaid response.
Put your checks in the mail.
So, that's right. Well, I have to watch that, Ron, because I'm running out of checks. The tube shields that will remove the heat when the RF shielding is heated, these types should be employed. So I'm going to give you a little lesson on that. Number 1, 2, 3, and 4. Number 1 is coated inside and out flat black with fingers inside to press against the sides of the tube. What are the fingers for? It's made out of metal. Metal is a very good conductor of heat, right? You take the temperature of the outside envelope of the glass, you physically touching it with metal, the metal conducts it to the outside perimeter of the shield. It's flat black, lovely black body radiator, and it radiates the heat, right? Number 2, same thing except it's for a 7-pin. Number 3, where you find all of them, shiny, shiny metal inside and out. They probably do their job in shielding you from whatever spurious emissions, but they don't do a good job of dissipating the heat. Number 4, this was from a Cosmophone 35, Richard. This is the same thing as a number 3, except it was painted black on inside and out. Didn't have the fingers to physically touch the tube, but it was certainly more effective than number 3. This is what the insides look like. 1, 2, 3, 4. Notice number 3 is shining on both sides. It's amazing. Up in the upper right corner, right there, this is the industrial strength type. This has many small fingers, not just a plate that rubs up against the tube, but many small little fingers that rub up against the tube, so that the end effect is there's an increase in the amount of area that is in contact with the glass envelope. And of course, it's painted black inside and out, and it's really, really handy because there's a handle on the top to pull the thing off. I think that's really neat. Nick showed me that one. Plate voltages. Obviously, higher input plate voltages will generally result in higher plate voltage. Input is higher, output is higher. If the output is higher, then it gets distributed around a radio and everything else is higher. Boat anchor equipment generally did not regulate or control the plate voltages levels. So if the tube was at or near its max ratings, then with the new voltage level, it's now over the max, and again, the tube life is compromised. Why? If it's over the max, it's probably still functioning, but it's getting hotter, right? Note that for solid state equipment, forgive me the little introduction there. Solid state equipment, the internal regulators generally ensure that critical voltages are held constant regardless of the input AC power. TR7 is a prime example of that. There's regulators all over that radio. Resistors have two characteristics, the value in ohms and the wattage rating. If the voltage rises, the heat rises, and oftentimes the capacity of the resistor is exceeded. What happens when you have too much wattage in a lower wattage resistor? You make smoke. How do you fix it? You replace it with one that has smoke with a little bit bigger capacity, right? Drake does that too. The Drake power supply, I'm telling you, that was done on a Saturday night around 11:30 because they took the day off. The typical application, the need for a lower voltage uses a large wattage voltage dropping resistor to determine the load voltage, increase the overall voltage, and the load behind the resistor changes. Drake uses this a lot. Capacitors. These components are made with layers of dielectric sandwiched between layers of thin aluminum plates. Heat will dry out these devices, causing failure and shorting of the metal layers. What is another characteristic of an electrolytic capacitor that you need to realize? It's not sealed. Oh yes, it's got the aluminum can, but it goes through pins that are in that phenolic base, and it is not a sealed system. So it's opened up to the air, and it'll become contaminated. Ever have an electrolytic capacitor explode? Come on now. I see smiles. They dry out naturally as the seals are not perfect, but with the larger voltages, the process is enhanced greatly. An example of the voltage problem in a real radio. This is an R4B. On a variac, this column is the 6.3 voltage level. This is the plate voltage that was measured, and it was measured on the output tube, the 6EH5, which is the electronic equivalent to a hot plate. Input voltage, the 6.3 volt filament was 4.1 volts, 109.7 plate volts. Let's look at it at 120 volts. 6.3, 165. Okay? 6.3 volts on the filament is not bad. 125 volts, 126, 127. 127 is the standard's maximum, remember? That'll be 6.7 volts and 179 volts. The audio output tube in this example here is a 6EH5. You look up in the book, 6EH5, maximum plate voltage allowed, 150 volts. Let me see, 150 volts, that is smaller than all of this. So the tube is running beyond its published maximum. David, how many 6EH5s have you replaced in your R4B? Two, right. First time he turned it on, and then the second time he turned it on. And when you take that tube out, and you put it into your Hickok 6000 tube checker, and it says, oh, no, don't check me, I have too much gas. Why? The getter's gone. When they short out, they do make an interesting light display, though. So this is what we faced with. We faced with a design, in this particular case, that was very close to its maximum. it's damaging. So for a reality check, how can we use our older equipment without solely degrading the set? The answer is found, obviously, in the need to control the input voltage. So let's look at a transformer. A transformer makes sense. It's a voltage control device. Permit me to draw in front of you. Transformer. Some draw 3 lines, but for brevity purposes, we're going to use 2. This is the input. This is the output. For grins, let's just say this is 120 volts. And let's, for grins, say that this is 10 volts. It's obviously a step down transformer, right? What are some of the features of this transformer? Some of the features would be, well, if this is running at a certain kVA level, this would be running at a certain kVA level. The same kVA level. So when I'm winding this transformer, I have to wind this for the kVA rating of the primary. What does that do to a transformer? Makes it heavier, it makes it bigger, and it makes it more expensive, right? But this solves the problem. Because if I had 120 volts and my machine was designed for 115 volts, well, I could just wind this to 115 volts because this transformer, the voltage on the output is just a turns ratio multiplier of the voltage on the input, right? Now, I know, Ron, you learned that in the 3rd grade.
Yes, I did.
Because that was before they only invented wire that December.
I didn't electrocute no elephants.
That's right. It's sometimes the truth hurts. If you were looking at converting a very large load, then this is a viable, though expensive, solution. So you got, in my shop, in my newly expanded shop, which is right now up to the gills with stuff, I have 1, 2, 3, 4, 5 benches. All of them right now have patients that are on each of these 5 benches of various stages of illness. One's a TR7, one's a T4XB, one's a T4XC, another an R4B, and I think the other one has got a high voltage power supply for a Titan amplifier. So all of this goes into the transformer. So if I wanted to have a single transformer that would serve all of these various benches, I would have to have a pretty large transformer that would take that 120 volts that I would get out of my receptacle and convert it down to a usable, because of the time that it was manufactured, arrangement. But there are some other solutions. Let's look at those. The one on the left is called a variac. In the terms of electrical jargon, it is a auto transformer. It's a single winding, but you notice the primary, the input voltage, is on part of that single winding, and the variac has a slider, and you've seen how they work. It has a slider that goes up and down that single winding. If the slider is already down here, the slider is reading 0 voltage, so you have 0 voltage coming out of the output. If you go all the way up, you notice that if it got to this point, it'll be 120 volts, which is the input. If it got higher, since it's a magnetically coupled device, 4th grade, Ron? First grade. I'm sorry. you can get actually more voltage on the input. So it's got the best of both worlds. It's got less than the primary and more than the primary based on the position that you run. Okay? That works pretty good to do it. The important thing about that is that the kVA rating of the whole transformer is basically what does the primary need, which makes the transformer less expensive to manufacture. On the right, you'll notice, and I'll go back to my drawing here, and permit me to draw in front of such an august group. If the voltage looks like this on the primary, and the voltage on the secondary looks like this, then we say that the primary and the secondary are in phase with each other. In phase. That sounds interesting. Okay? Yes, it's technical. So that as the voltage on the primary rises, the voltage on the secondary rises. That's in phase. If the voltage on the primary would rise and the voltage on the secondary would fall, then this is called out of phase. Okay, that's fine. I have my handy dandy U-Testum colored pens. What happens if I start playing around with that wiring with no voltage applied to the primary? The standard transformer must have a capacity in both the primary and the secondary. We saw that. So if you have a 1 kVA load, each of the windings are rated at 1 kVA. For the variac, the rating is just for the single hole wiring. So per kVA, the variac is smaller, lighter, cheaper. If you have a shack that you have to provide where you have multiple outlets, a variac that would be for your whole shack would be very, very large, physically large, okay? It would work, but it wouldn't be a very economical solution. So let's look at a different way to solve that problem. If I take our transformer here, and I'm going to assume that for right now, the way the transformer is wound, I am going to connect this line to this line so that now my voltages are in phase. The resultant voltage would be this plus this. Does everybody see that? If that is the case that I have my transformer connected in, that is called a boost connection. In other words, I'm basically adding the voltage on the primary to the voltage on the secondary. So if I go back to my 10 volts originally that we said, then what I measure from here to here is 130 volts. It is a boost transformer. All right? For our purposes, that connection is not going to do us any good. We're heading in the wrong direction. So what happens if I take the connections and take advantage of this phasing business in the transformer? Let's redraw our transformer. And I do this. And I take my voltage from here to here. Then it's the primary voltage, secondary voltage, and it's the primary voltage minus the secondary voltage gives us the output. Because the connections are out of phase. That's called a buck transformer. I'm taking whatever is the voltage impingent upon the secondary, and I'm using that to reduce the voltage on the primary. Now, if I did that, remember that in this situation, the kVA rating of the primary does not have to be the kVA rating of the secondary. Does not have to be. It's just the way that we're connecting it. You can go home and try that. Try connecting them both ways. Little step down, step up transformer, step down transformer. You can connect it and you can do this buck boost experiment yourself. So if I wanted to take care of my whole shack, then I would probably want to use a buck boost arrangement connected as if it were a buck transition. Here's one right here. This belongs to my best neighbor. Primary voltage is 120 or 240 volts. Secondary voltage is 12 and 24, right? Secondary is smaller. kVA rating is a half a kVA. So if I connected this transformer on the 12 volt side, and I have 120 volt primary, 12 volt secondary, what do I have on the output? Subtract the two together, I have 108 volts, right? So this would work, and I can distribute that to several receptacles that is in your shop or your shack. So there's solutions to this problem. Since the issue at the beginning was voltage levels higher than the manufacturer's intended design, several choices. For the shack as a part or whole, where one device feeds several radios, it would seem that a single transformer connected in a buck mode would be, I didn't invent this language, would be advantageous. Care must be taken to ensure that the primary circuit protection for each load is present. You can't assume that this protection circuit on the primary is going to be protecting everything downstream. You have to have circuit protection downstream. Okay? In the case of the single unit for the bench, you're working on a radio, then this probably doesn't make a whole lot of sense. And the variac does. Just make sure you don't bump the dial. Questions? Too much information after lunch? Yes, John.
When you have voltage sag, which people see, I do because I've got a shopping center up there and sometimes loads kick in and that voltage drops down. So now you're going to undervolt that equipment that you want to get out 108 volts.
That's correct.
What do you, I mean, undervoltage is as bad as overvoltage because the current drops.
The guy that the Nobel Prize was named after invented trinitropentylene, TNT. I would suggest a judicious application of that would help solve your problem. Now, I didn't say that, John. There is no protection in a sag like that. The power company does have regulations that determine what is allowed sag-wise. But there is no protection that you can do other than changing the tap, or if it's on a variac on a 1-to-1 ratio, just monitor the output voltage to where you need it. Now,
When air conditioners, I don't have one, but my neighbor's stuff kicks in, and, right at that moment when it kicks in, you can watch the voltage.
yes, but it's momentary. I mean, it's probably less than a cycle or two.
Probably, depends how long the line catches up with it.
Well, remember that the line feeding your distribution in the terms of electrical utilities is very stiff. which means that any changes in voltage is going to be almost unnoticeable because of the inherent built-in capacity of the lines. By the time it gets down to you, it has gone through several transformations. Every time it goes through a transformer, you get a built-in device that helps smooth out the variations in the loads. So now, will you continue getting them? Yes. Can you really do anything automatically about it? You can. There are automatically variable auto transformers. I think that trinitro-toluene is a better solution.
I found that out when they built a shopping mall about a mile from my house. And every once in a while, I don't know whether it's just the timing of some of the equipment there, like the giant air conditioners and all these things like that. You can watch the kilowatt drop voltage per second.
John, I've been telling you this for years. You just simply need to move. Yes, Ron.
The buck boost transformer, your secondary current rating is equal to the primary current rating?
No, it is not.
Current rating,
No, it's not.
okay?
The output, the combination of the output that you have here is shared by the primary and the secondary. This KVA does not have to equal the primary KVA because it's shared. The primary is,
Never said that.
what did you say?
Current rating. Current.
Size of the wire.
The current rating of the secondary is not having to be the current rating of the primary.
It's gonna be bigger every time.
Not the power rating, current rating.
Yeah, that's right.
Okay, so what is the ratio?
Depends upon this turn ratio and what's the overall KVA rating of the primary. Let's see if this has any data on it. It doesn't give it to me. In this particular case, this is made in Mexico, so I really can't tell you what it is.
Habla español.
The current rating on the secondary of a filament transformer is usually way higher than the current rating of the
Yeah,
primary.
the current rating. Yeah, so if this was,
We're not talking about a filament transformer. We're talking about.
well, but you're talking about a standard transformer that if you were using the primary solely connected to the source of power and the secondary solely connected to the load, then this, if it was in a step-down relation, this current rating would likely be higher than this current rating because the KVA rating of this would be the KV rating of this.
Okay,
So the capability of the secondary in a step-down arrangement, the current capability would be higher.
Any filament.
current capability of the secondary would be higher?
You would have to consider
In
the
a step,
rating of
in
the
a,
secondary.
yeah, that's correct.
But any filament transformer could be a buck boost transformer, it's just how you hook it up.
That's correct.
And therefore, the current passing through that secondary, which is typically a much larger wire, much higher capacity, amperage capacity, would be insignificant to the secondary. The secondary,
Well, it has the capability, I mean, inherent to the construction of the transformer, the secondary would have a capability of higher current.
right. which
But
would
that
be
doesn't
unneeded.
mean that it's higher current.
No, it'd be unneeded.
So, back to my question. The secondary of a buck boost transformer, we're not talking filament. Because filament transformer usually means half amp on the primary and 10 amps on the secondary, roughly. So
Okay.
the buck boost transformer, the 500 kVA rating of that transformer is the primary rating?
No.
Or is it?
We're mixing our uses. In a transformer, where you have the role of this device to take a primary voltage and go up or down on the secondary.
Correct. We're talking about
The
going
two
in-
windings, the only coupling in the windings is a magnetic coupling. It's not a winding like that, okay? If you have a primary transformer voltage and a secondary transformer voltage, the KVA rating of the primary is the KVA rating of the secondary. Now, if it's a step down where the secondary is less than the primary, the KVA rating is the same. But the voltage and the current on the secondary would be different if it's a step down.
Correct.
The step down is less voltage, more current. That's why you need 45 amperes on your honky tube that you got in your amplifier.
60.
Oh, excuse me. I didn't mean to denigrate your tube.
Okay, let me see if I understand this correctly. When we put it in the boost mode, okay, we are boosting the AC line by the secondary voltage.
It's correct.
Okay,
You're in phase and you're adding the voltage of that waveforms together.
in phase really is yes, you're in phase with the secondary, with the primary.
Yes,
Okay,
that's in the boost mode.
correct.
Yeah.
So if that primary draws 1 amp, how much current is drawn in the secondary?
It depends on that ratio. Whatever power you're drawing out of here is going to be the power that you draw out of the combination of these two. Not just this one only.
Why am I drawing power out of the secondary?
Well, because you are a citizen of the earth, and that's the way. That's the way God made it.
So essentially what you're saying is that I have to supply the same current rating as the primary.
No. We're not building a transformer. If I build a transformer to step up or step down, okay, I have no interconnection in the windings,
Right,
all right? The KVA rating of the primary and the secondary are the same.
yes,
The KVA rating, not necessarily the
Correct.
current rating, okay?
correct.
Now, I'm interconnecting the two together. And if I interconnect the two together where the primary and secondary are in phase, then that is a boost transformer. So I'm adding the waveform of the primary to the waveform of the secondary. That does not mean that the secondary is going to have the same current flowing through it as the primary, because I'm still magnetically coupled. The number of turns is different on the primary than it is the secondary.
So the current rating of the secondary depends on the load.
The current rating of the combination depends on the load.
Yes, but the secondary is where you are adding voltage, correct? To the primary.
No,
Or
you're not adding voltage.
you're either adding or subtracting, you're in a buck or a boost.
Oh, okay, in that sense. I'm not doing that. The magnetic coupling is doing it. That's correct.
Correct.
I had to state that.
David, the only liability is if it's in a boost, the secondary voltage can't meet the insulation of the secondary, its voltage rating might exceed the capacity of the insulation. The voltage may, because
Okay. No,
The rating, the core is ground, if you will.
I understand. Most of these transformers are Class H insulation. There is no cost advantage. As a matter of fact, there's a cost disadvantage if I use different insulation values for both the primary and the secondary. So in a regular transformer configuration, if the voltage of the secondary is less than the voltage of the primary, the wiring type is the same. So if I have a certain rating of current capability maximum on the primary, that's the capability on the secondary, only because it's not there, but it's the same type of insulation. So you may have inherently the capability of the secondary to have a larger amount of current going through it.
Take it to another extreme, if you have like a Tesla coil or a spark coil on the car, all right, that insulation on the secondary, because it's higher voltage, has to be, if you will, higher than the primary insulation.
That's a step up.
Yeah,
It's gonna step up
That's
the
right.
situation.
that's correct. And so what they do is they figure out what the transformer is going to be, and they use that type of wiring.
Exactly.
And it's generally the class of type H wiring, which has a very high dielectric wrapping on the wiring.
Brother Dave, I have two questions for you. I didn't go to the same classes that Ron did. We started off this discussion talking about the variable input AC voltage and how it affected our lower secondary voltage. I don't see that this, if the voltage goes up on this, whether it's buck or boost, it's also going to change our secondary.
That's correct.
So we're not doing any necessary
Well,
stabilization.
What we need to think about is that the change of the primary voltage over time is going to be tiny. Now, in the case of John's shopping center load that he has, I mean, his solution is to move, because there's no way that you're going to get a passive device like a transformer to compensate automatically for that. Now, they make devices that'll do that.
Well, that's what my next question. What about a UPS?
Well, a UPS is not going to do you any good unless you have a requirement that the voltage has to never fall to zero. But a UPS, if you just look at the inverter, which remanufactures the waveform on the primary, then if there is a way to inject additional energy on a sag, it helps to keep that voltage output. But the cost of a UPS type of system is far greater than a simply wound transformer.
Okay, thank you.
The issue, yes, Dallas?
Would a solar transformer resolve this?
No, because they're wound the same way. Solar is a manufacturer of transformers. And many solar manufacturers, S-O-L-A-R, many solar manufacturers are manufactured in the buck or boost configuration. Solar is simply a manufacturer.
Is that capable of being switched from buck or boost?
Only if you take the wires and switch them.
Yeah.
Or you can do some kind of a switching arrangement, yes. Yes, Mr. Ron?
I think what he was talking about is a ferro-resonant transformer. And that's solar makes ferro-resonant
Yeah,
transformers.
so does many. Sorgel makes them,
Right.
many of them make it.
Problem is, they draw power whether they got a load or not.
Correct.
Well,
They don't draw as much, but they do consume power.
the way that the transformer is wound is that the output voltage is more or less the same than the input variation on the input voltage. And they do that magnetically. It's a different type of wiring, different type of winding on the voltage.
I want to attend your lecture when you explain that.
Ferroresonance? Well, I'm still in school and I hadn't had that class yet.
Maybe Ron had that in his school.
Yeah, he did. He got that in 5th grade.
So rather than pay $100, $150 for one of these, I can take one of the old filament transformers out of my junk box and make it a buck boost.
Correct.
You can. Within the current rating of the primary, you can do that. Yes, that's correct. You can. Because that transformer was wound with the primary and secondary independent of each other,
That's right.
except magnetically.
Yeah. Oh, they gotta be.
Okay. Let's see. Thank you. We need to move this table?
No, CAT is either.
All right, the idea, of course, is we don't want to blow up our little bitty tubes. They're getting to be expensive to replace, especially because the audiophiles keep going after them. And I don't know if you've priced a 12AT7 lately, but they can go anywhere from 20 to 40 bucks a piece, and which is kind of hard to believe when you used to be able to buy them for $1, you know. So, in any event, we want to keep, and they operate much better with lower voltage, so longer life. We're going to take a break right now as Bob Heil gets set up for the next presentation. So why don't you all take about 10 minutes and we'll get back.